ast-grep rewrote tree sitters see runtime in Rust. I set the direction, constraints, and experiments. ChatGPT wrote, tested, and profiled most of the implementation. The result looked excellent. Raw parsing was almost 30% faster. Reading the completed tree improved too, and the generated language ecosystem still worked. Then I connected the new runtime to ast-grep and ran it across a real TypeScript repository. The application became slower. The parser benchmark was correct. It was also incomplete. This is the story of how a successful parser optimization failed at the application boundary and what it took to make the improvement real. To explain why, we first need to look behind the headline. Source code looks like text to us. A function has words, punctuation, and indentation arranged across a file. Many coding tools need a different view. They need to know that one name is a function call, another is a declaration, and a pair of braces belongs to one particular block. That information lives in a syntax tree. TreeSitter turns source text into those trees. It recognizes tokens, applies a language grammar, and preserves the exact structure of the original program. The result is concrete enough for an editor, a search tool, or a coding agent to navigate and change code without pretending it is ordinary prose. TreeSitter began in the editor world, where syntax highlighting and navigation must keep up with typing. Today, it has become a cornerstone of modern coding infrastructure. Editors, code search, refactoring tools, indexes, and language-aware analysis all build on its syntax trees. The same is increasingly true for agentic coding tools. An agent may generate text, but useful coding actions still need exact language boundaries. They need to locate a function, understand a call, replace one expression, and verify the result across many languages. TreeSitter provides a shared parsing layer beneath many of those workflows. That makes changes to its runtime important far beyond one benchmark. ast-grep is a structural code search and rewriting tool. Instead of asking whether a file contains a particular string, it asks whether the syntax tree contains a particular shape. That lets a rule distinguish a function call from the same text inside a comment, or replace one expression without touching a similar-looking declaration. Before ast-grep can match anything, every source file must pass through TreeSitter. I could make rule matching faster, prune irrelevant nodes, and cache configuration. But parsing still happened first. As ast-grep improved, TreeSitter became both its foundation and its performance ceiling. For years, rewriting the core sounded useful and unreasonable in equal measure. Before AA, rewriting TreeSitter was not mainly a matter of translating C syntax into Rust. TreeSitter carries several large responsibilities at once. It supports many programming languages, including languages that add their own custom scanning code. It must parse valid code quickly, recover from incomplete or broken code, and handle grammar ambiguities correctly. It builds syntax trees, stores them efficiently, and exposes them to tools that need to navigate every node. For editors, it also supports updating a tree as the user types and reporting what changed. And all of this sits beneath an existing ecosystem. Generated parsers, language bindings, editors, and tools already expect the runtime to behave in particular ways. These responsibilities are connected. Changing how the tree is stored can affect parsing speed, memory use, editor behavior, and downstream tools. That is why a rewrite had stayed on the shelf. For one person, preserving all of those promises at once was a Herculean task wearing a header file. Then AI-assisted rewrites showed that the experiment had become cheap enough to attempt. So I asked ChatGPT to attempt it under one simple rule: change the language, not the behavior. Generated TreeSitter languages are already compiled artifacts. They expect particular symbol names, calling conventions, and data layouts. Together, those promises form the CABI. Changing the implementation to Rust did not give us permission to move that boundary. The public layouts stayed C-shaped. External scanners stayed compatible. Existing generated languages did not need to be regenerated. Behind that boundary, private Rust code could change. The final runtime is narrower than upstream TreeSitter. It always parses fresh file snapshots. Incremental reuse of an old tree was removed, along with native loading of grammars compiled to WASM. Many raw pointers and unsafe blocks remain where compatibility requires them. This is not a one-for-one upstream replacement. It is a runtime aimed at ast-grep and coding agents that analyze complete files. ChatGPT migrated the runtime like a dependency ladder. First came allocation helpers, source positions, recovery costs, and Unicode decoding. Then came subtree, treesitter's underlying representation for syntax trees. A subtree value can represent a token leaf or parent containing child subtrees. Above that came generated language tables, then lexing, then the GLR stack that stores active parse histories. The public tree, nodes, cursors, and changed ranges followed. The parser and reduction loop moved last because it coordinates everything below it. At each layer, the Rust stayed close to the C-tests checked behavior. Real grammars checked compatibility. ast-grep checked integration. Eventually, Rust owned the active runtime. It compiled, passed the tests, and parsed existing languages. Naturally, I immediately asked for more. I gave ChatGPT one broad autonomous objective: improve performance by 20%. The run continued for several days and nights. It profiled, implemented, measured, and kept going. Eventually, the benchmark crossed the target. But each result added another layer of ownership tricks, layout experiments, and fast paths. Every patch looked plausible by itself. Together, they grew faster than I could build a reliable model of the runtime. Then the parser began segfaulting inside unsafe Rust, in code that still relied on raw pointer operations. There was no friendly Rust panic and no failed assertion. The process simply left, somewhere inside code neither of us could fully explain. A parser that is 20% faster and occasionally disappears is not an optimization. I reverted the entire performance run. The 20% disappeared with it. The next objective was not speed. It was local reasoning. First, I reduced the runtime to the workload we actually needed. Incremental old tree reuse and native WASM grammar loading left the hot implementation. External scanners and generated language compatibility stayed. Then, ChatGPT performed a second rewrite, this time for humans. Internal raw pointers became references or slices where their lifetimes were clear. Sentinel pointers became explicit optional states. Out parameters became return values. Large modules split around their responsibilities. The compatibility boundary remained deliberately C-shaped. The private runtime became easier to explain. Now a failure had an address in the architecture. We could ask who owned a syntax node, which references survived arena growth, and why one reduction created temporary state only to delete it. Only then did performance work resume. To understand the optimization, we need a small model of the parser. Start with the source expression, count plus 1. The lexer reads its characters and groups them into tokens. Count becomes an identifier. The plus sign becomes an operator. 1 becomes a number. The parser does not decide what every character means directly. It receives this token stream from the lexer. Each token also carries its position in the source. Those positions let the final syntax tree point back to the exact bytes that produced it. With tokens available, the parser can begin interpreting the grammar. Treesitter's parser is based on LR parsing. An LR parser keeps a numbered state and a stack recording the path that reached it. It also examines one look-ahead token, the next token waiting to be processed. The generated parse table combines those two values. Current state. Next token. The selected table entry tells the runtime what to do. In the ordinary case, it gives one valid action. That action might shift a token, reduce several recognized pieces into one larger construct, accept the completed tree, or begin error recovery. The important point is that the parser is not guessing. It is interpreting a table generated from the language grammar. The simplest action is shift. Suppose the lookahead is the identifier, count. The parser consumes that token, attaches its syntax value to the stack, and enters the next numbered state. The lookahead then advances to the plus sign. Shift means this token is valid here, remember it, and continue. The stack records two things together. Parser states describe where the grammar can go next. Syntax values record what source has already been recognized. As long as the table keeps returning one action, one stack path is enough. Reduction recognizes a larger grammar rule. After shifting count, plus, and 1, the table may report that these pieces form an addition expression. The parser walks backward over the corresponding stack entries and collects their syntax values as children. It creates one parent syntax node for the addition, then pushes that parent in the state selected by the grammar's Godot table. The parser stack and syntax tree are related, but they are not the same object. The stack is temporary control history. The syntax tree is the result being built for the caller. Reduction sits directly between them. It removes recognized history from the stack and preserves that syntax underneath a new parent. For many inputs, every table lookup produces one valid action. Real programming language grammars are not always so cooperative. A table entry may say that both shifting and reducing are valid. The correct choice may depend on tokens that have not arrived yet. Choosing immediately could discard the interpretation the rest of the file requires. This is a conflict. Instead of guessing, treesitter keeps both possibilities alive. The shared past does not need to be copied. Only the possible futures need separate identities. That is where generalized LR parsing begins. GLR stands for generalized LR at a conflict. Treesitter creates several active stack versions. One may shift. Another may reduce. Each version names a possible future, while their common past remains stored once. That shared history forms a graph-structured stack. Separate heads point backward into common nodes. Links between nodes carry the syntax recognized on each step. As more tokens arrive, one version may fail and be released. Several may remain valid. Compatible versions can also merge when they reach the same state and position with equivalent recovery and scanner state. GLR is what lets treesitter handle genuine ambiguity without copying the entire parser history for every choice. The graph has a real job when the parse forks. That is enough parser theory. Now return to the Rust rewrite. After reverting the unstable 20% attempt and making the runtime readable, I changed the optimization process. Instead of asking ChatGPT to make the parser faster, I asked it to measure one expensive operation at a time. We began with reduction, the operation that moves recognized syntax from the temporary parser stack into the subtree representation. The allocation profile counted more than 1 million logical stack nodes across 40 fixtures in 7 languages. Of the release nodes, 98.898% had exactly one predecessor. The mean predecessor count was only 1.011. And the runtime had written about 127 megabytes into inline link slots that were never used. These numbers did not mean that 99% of parser time was deterministic. They described the shape of the stored histories. That shape was overwhelmingly a straight line. Treesitter needed a graph for genuine ambiguity. But ordinary parsing was paying to allocate graph nodes, initialize link storage, and maintain reference counts before a fork even existed. The generalized structure was waiting for a conflict that usually never came. Now the rewrite had a specific target. Preserve full GLR behavior, but stop building its graph before the input actually needed it. The correction was a deterministic window. While one parse history remains active, the parser stores a compact linear path. Shift extends that path. Reduction walks backward through it directly. Only when the parse table presents a real conflict does the runtime materialize the full graph and continue with ordinary GLR behavior. The fallback did not disappear. It moved behind the event that required it. Correctness mattered more than the shape of the fast path. Error recovery, external scanner state, version merging, and ambiguous reductions still had to match the original runtime. Across the 7-language benchmark, this change improved parser throughput by about 9%. JavaScript, Python, Rust, and TypeScript gained the most. Ordinary parsing had stopped paying the full price of rare ambiguity. This was the first major performance improvement retained after the full revert. One measured mechanism, one explainable change, and a 9% parser win. With the stack faster, the next profile pointed at syntax storage. The old design used compact 8-byte values, but many full leaves and parent nodes still required separate heap allocations. An arena could serve many nodes from one growing block. That sentence concealed several independent decisions. How nodes are represented, how children are stored, how references survive movement, and when shared syntax is released. Many reasonable versions lost. A direct Rust enum doubled the compact representation to 16 bytes and made parsing almost 20% slower. Premature garbage collection reduced throughput by more than 37%. Removing reference counts appeared 8% faster, until tests showed that shared syntax could be released too early. The retained design used 4-byte tagged offsets into a growable arena, with different ownership rules while parsing and after publication. For a moment, the parser benchmarks looked excellent. At the combined checkpoint, the Rust parser was roughly 30% faster than C. Then I built ast-grep against it and ran the open code outline workload. The tool parsed every TypeScript file in the repository and walked each completed tree to extract an outline. The Rust-backed application was slower. The parser benchmark had reused one parser. It measured already loaded source, returned a tree, and stopped. ast-grep also created and configured parsers across thousands of files, managed arena memory for each lifecycle, and read every tree afterward. The benchmark had measured the middle of the journey and called at the finish line. So the instruction changed again. Stop optimizing the parser in isolation. Profile construction, parsing, traversal, memory, and the complete application. The first arena was built directly on the operating system Z virtual memory. It reserved 4 GB of address space with memory map, committed small chunks as needed with memory protect, and released the mapping with memory unmap. Only touched pages became resident memory, so the design looked cheap in a micro-benchmark that reused one parser. But ast-grep created a parser for each file. Across 2,311 TypeScript files, the trace showed 2,329 memory maps, more than 10,000 memory protect calls, and 2,305 memory unmaps. Matching reservations to releases revealed 2,291 complete 4 GB arena lifecycles. The parser had become an enthusiastic virtual memory benchmark. The fix was ordinary construction. Begin with a small header, allocate 256 kibibytes for the first syntax record, and grow only when needed. That removed the syscall storm. Then memory became the next failure. Early arena growth copied live bytes into a larger block, while keeping old blocks alive so raw addresses remained valid. On the TypeScript stress corpus, those retired generations pushed peak RSS to 1.04 GB. Relative offsets made reallocation safe and reduced the peak to about 492 MB. Still far too high. We tried reclaiming dead syntax nodes. Then we restored exact reference counts and node-free lists. The peak barely moved. The diagnosis was wrong. Allocation counters showed that temporary child array capacities had advanced the arena by 468 MB. Everything else combined was about 2 MB. The retained fix reused those temporary buffers by exact capacity once a parse grew large. Peak memory fell to 91.2 MB. Parser throughput decreased by about 1%. I kept the trade. We had paid 1% to avoid almost a gigabyte. Memory was under control, but construction was only half of the tree's career. 4-byte offsets reduced traffic while building syntax. Readers now had to add the arena base whenever they accessed a node. The parser benchmark measured the benefit n, stopped before paying that cost. So we added a traversal benchmark. The first index design was slower to read. After tightening record layouts, the full traversal recovered. A narrow tree cursor cache then resolved one parent's child slice once instead of repeatedly. Traversal improved by more than 5% against the preceding Rust revision. ast-grep also began reusing parser instances across files. That removed repeated language setup and exposed new hotspots in parsestable lookup, action dispatch, and lexing. Direct lookup indexes, a fast path for one parser action, and a guarded ASCII path addressed those costs. Every retained change had to survive both its local gate and the application. After the lifecycle and read-side repairs, we repeated the comparison with C. Raw parser throughput was 29.74% higher. Tree traversal throughput was 10.16% higher. On the open code outline workload, ast-grep used 22.2% less user CPU and finished 21.6% sooner. The output was byte identical. Peak RSS increased by 7.91 MB. The memory trade-off is real and it belongs beside the speed result. The lesson is not that Rust automatically beats C, or that AI can safely rewrite any mature system. AI made the exploration dramatically faster. It did not decide which result was correct. Faster is a claim about a workload, a lifecycle, control revision, and the costs the benchmark includes. The rewrite made the runtime easier to change. The experiments made it harder to fool. That was the real optimization.